All right. Welcome back, I assume. This is going to be problem set 7. It's based on our homework number 7. And to start off, we've got number 1, and we want to find the exact values of f at these given numbers if we're told that f of x is equal to negative cosine of x. And so in order to do this, obviously this is f prime of these given x values, and that f prime, as we know, means that that's the derivative of f. So the first thing that we want to do is we want to find whatever the derivative of f of x is here. Well, according to our textbook, and obviously several other sources, the derivative of, so we can represent the derivative with respect to x like this. So the derivative of cosine of x equals negative sine of x, just like the derivative of sine of x is always going to be cosine of x. These are two really important derivative rules for us to remember. We're gonna have a really fun time with memorizing all of our trig derivative rules. There's quite a few of them. There's one for every type of trig value we have, including our inverse trig functions, but we won't get to those for quite a while. But so it says the derivative of cosine of x equals negative sine of x, and this negative right here, we know that's a negative 1 times cosine of x is another way we can write that. So this is just a coefficient. It's not part of our derivative at all, because if we have a constant coefficient, we keep that in front of our derivative. So what we're going to have is we're going to have negative 1 times whatever the derivative of cosine of x is, which is negative sine of x, which tells us that the derivative of f, these negatives cancel out, and then it's just 1 times sine of x, so it's just sine of x. I'm going to erase this bit so we've got space for other things, and I'll rewrite that up here. So our derivative of f is sine of x. So now it's really easy. We've got, we want to find the value of the derivative of x, the derivative of f at negative pi over 2, which means we quite literally just plug that into this right here. So f prime of negative pi over 2 is equal to sine of negative pi over 2. Now, this will be made a little bit easier as long as we know our unit circle, which I'll kind of sketch over here. This is going to be a little bit of a messy sketch, so don't put too much focus on it. Let's see, it's going to be about there and there. So we know this is pi over 2, pi, 0 or 2 pi, 3 pi over 2. Let's see, we've got pi over 6, pi over 4, pi over 3, 2 pi over 3, 3 pi over 4. I just think it should be 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 4. What comes next? 5 pi over 3. Should be 11 pi over 6 and 7 pi over 4. Okay, so here's our unit circle. We want a negative pi over 2. So instead of going this way, we're going the other way because of that negative. So we go negative pi over 2. So this is going to be the same as sine of 3 pi over 2. You see that because we went negative this same distance there, which places us here. And our sine value at this point we know is negative 1. So this, our answer is just negative 1. Let's try, I'm going to erase this now. One moment. Erase this, erase my arrow. Oops. Oh no. Okay. It gets so weird when I start erasing sometimes. I did it again. What? I don't... Okay, I just don't want to erase my little 2 pi. Okay, now, same thing. If we have f prime of 15 pi over 6, that's the same as sine of 15 pi over 6, because our f prime is sine of x. So 15 pi over 6, we can clearly see goes around our unit circle at least a couple of times. So let's see, if it's over 6, I know that 2 pi, which would be that first rotation, is equal to 12 pi over 6. So I'm going to take that out of my 15 pi over 6. So that tells me that this is the same as 3 pi over 6 once I take that out, which is just, well, that's just the same as pi over 2, isn't it? Is that right? Hold on. Let me let me just double check that for a second. Let me just make sure I'm thinking what I think I'm thinking. Yeah, so we go full circle, which is that 12 pi over 6, and then we go 3 pi over 6 forward, so we go 1, 2, 3, which places us at pi over 2. So this time it's just sine of pi over 2, which we know is 1. So that's a 1. Let's try... I might not have set these questions up the way I meant to, but that's okay, because I think we're still getting the gist of it. So let's try for this next one. So f prime of 35 pi over 4 is equal to sine of 35 pi over 4. And I know that if I take out my multiples of 4, that gets me up to 32 pi over 4, right? So I'm going to take that out of there because I know that this is 8 fours. So this bit right here is the same as 8 pi, which is just 4 rotations around our unit circle. So I'm going to take that out, and I'm left with a 3 pi over 4. So we're actually working with sine of 3 pi over 4, which we know is right up here, which we know from our unit circle is going to be equal to the square root of 2 over 2. Okay, and then the last one that we've got going here is f prime of 5 pi. And of course we know that 2 pi is 1 rotation. I know that 4 pi would be 2 rotations. So I know that that's 2 rotations and then 1 pi. So I go around once, around twice, and then I go 1 pi, which lands me right here at pi. And we know our sine value at pi is going to be 0. So our answer is 0. All right. Let's take a look at this next one. It says if f of x is equal to 4 times e to the x, we want to find the derivative at these x values. And this seems really intimidating. E tends to be a little intimidating for a lot of people. But it's really no different than like if we had like pi or whatever, and e is actually easier for us to work with. So again, in our textbook and elsewhere, of course, the derivative of e to the x is just e to the x. It's really simple. It never changes. It's just this. So if we have 4 times e to the x, and we want to take the derivative of that, remember, this is a constant coefficient. So it's just 4 times the derivative of e to the x, which is just 4e to the x. Doesn't change. So if that means our f prime is the exact same, right? We just plug this value in to here. So if I have f prime of 1/2, that's going to be 4e to the 1/2, which is just 4 times the square root of e, based on our exponent rules, right? If I have f prime of 7, that's just going to be 4 times e to the 7th. That's all we have to write. And then this next one is a little bit of a fun one. So it's f prime of natural log of 12, so it's going to be 4 times e to the natural log of 12. And so the really fun thing here is that because this is an e to the natural log of something, right? So it's a log base e to the 12. That's the same thing as this. Because it's to the power of a log with the same base, those actually cancel out. So e to the natural log of 12 just turns into 12, which means that if we have 4 times e to the natural log of 12, we have 4 times 12, or just 48. Let's come down to number 3. This one's a little bit of an interesting one. So they give us that f of x equals this quotient here. So 3x plus 4 over x minus 2. We could use quotient rule for this, but that's clearly not how they want us to go about this. So we want to define it using 2 different definitions for our derivative. This first one is from our earlier chapters of our book, which is what we've been doing for this past unit, leading up to our midterm. And the second one is from the next chapter. They are effectively the same thing, and they will result in the same thing, which I'll show you here in a moment. So really, as long as you know one of them, you should be fine. But just try to remember both of them in case we need to at any point. So in this case, we want to define the derivative of this using this definition here, which is one we're pretty familiar with. So I'm going to plug that in over here. I'm going to write it so it's the limit as t approaches x of, let's see, so it's f of t, so it's 3t plus 4 over t minus 2 minus 3x plus 4 over x minus 2, right? Because that's our f of t minus our f of x all over t minus x. And this is that definition, but as we can see, they want us to simplify it so that we don't have any complex fractions. And a complex fraction is when we have something like this, where the numerator or denominator of our fraction is a fraction in itself. So we need to get rid of this fractional component here. And so let's kind of work with this. We'll manipulate it a little bit. Whenever I see this, I know that the first thing I want to do is just to combine this into one fraction. So I'm going to find that common denominator by multiplying that across. So let's see, we get x minus 2 times t plus 4 minus, we're going to get t minus 2 times 3x plus 4. Oh, there should be a 3 here. And then that's all going to be over common denominator, so we're multiplying those together. T minus 2 times x minus 2. And then that's all over t minus x. We've done this a lot, although this one's a little bit trickier now because there's just more happening. And what we're going to do is we're going to go ahead and FOIL these out and then combine any like terms. So I'm going to FOIL this out to start. So you've got x times t, so it's an x times t times plus 4x, and then minus 2t minus 8, okay? And then I know that we're going to be subtracting whatever this is FOILed out, so we're going to FOIL this out as well. Going to do, let's see, that should be, oh, wait a second, I messed up something in there. Whoopsie. Let me go back. Go back. I'm going to rewrite this actually because I made a mistake. I corrected a missing 3, but I put it in the wrong place. So let's see, we found that common denominator. So it's x minus 2 times 3t plus 4, there we go, and then a t minus 2 times 3x plus 4. There we go. And you'll see that I'd forgotten the 3 there, and I'd accidentally put it in there to make up for it, which doesn't make sense. So that's my bad. Sorry about that. I hope that wasn't too confusing. And now, like I was doing before, we're going to FOIL this out. So we've got 3xt is how I'll write that, plus 4x minus 6t minus 8. And then, like I said before, we're going to subtract whatever this whole bit is here. So we're going to FOIL this out as well. So we get a 3xt plus 4t minus 6x minus 8. And so I'm going to write it above here. I'm going to rewrite this. So we've got 3xt, and then I see we've got a minus 3xt. So I'm going to write that there, and I know those cancel out. I'm just going to block them off there so we show we've done them. Then I've got plus a 4x, so I'm done with that. And then I see I've got a minus 6x, so I'm going to write that there. Oh, nope, sorry. I know I'm subtracting a minus 6x, so I'm going to add a 6x there. And then I've got minus 6t minus positive 4t, and then minus 8 minus a negative 8, so it's going to be minus 8, it's plus an 8, so those cancel out. So now we've just got these terms, so I combine that, that's a 10x minus a 10t. So I'm going to rewrite our limit now to show that. So we just got that this is a 10x minus 10t over t minus 2 times x minus 2 all over t minus x. All right, we're seeing some progress now. This is a little bit easier for us to work with now. So let's see here. We want to get this top bit in the form of t minus x so that we can cancel that out. So get rid of that fraction line there, or the complex fraction rather. So I'm going to factor out a negative 10 from this. So that'll get me a negative x minus a negative t, which is the same as a negative x plus a t, right? With that negative 10 on the outside. And then I can just flip that around. So it's a negative 10 times t minus x, because addition we can just flip-flop. And that's over t minus 2, x minus 2, and then t minus x. And I see these cancel out. So now I'm left with, as t approaches x, I've got a negative 10 over t minus 2 times x minus 2. And we see it's still a fraction, but that's okay. It's no longer a complex fraction, so that's what we wanted. So that's what they want in here. Let's see, that was a negative 10 over t minus 2 times x minus 2. So look at that, we've managed that. And if we were to plug in, if we were to actually solve this limit, right, so as t approaches x, I'm going to plug in x for my t. That gets me, I'm going to write over here, an x minus 2, obviously times an x minus 2, which gets us a negative 10 over x minus 2 squared. And if we know the quotient rule, which we'll have to use later, so I hope that we know that. But if we know the quotient rule, we can double check that with this, and we will get the exact same thing. I've done it already. Now, for this next part, we want to define the derivative using this definition. This time, they don't want us to simplify, so we are allowed to have complex fractions, remembering that our f of x is equal to this up here. So it's an f of x plus h. So it's going to be wherever there's an x, I plug in an x plus h. So it's going to be 3 times x plus h plus 4 over x plus h minus 2. And that's my first term. So then I've got minus an f of x, which is just 3x plus 4 over x minus 2. And then it's all over h. And notice this time it's not and like up here, it's a t approaches x. This time it says h approaches 0, which is why this is so different. And obviously they don't want us to simplify, but I do want to work through that with you just so that we can see how to simplify that for when we do need to, and so that we can see that these do end up being the same. So let's see, it says the limit as h approaches 0 of 3 times x plus h plus 4 over x plus h minus 2 minus 3x plus 4 over x minus 2 over h. And so the trick here is that obviously we need to get rid of this h in the denominator because it would get to 0. So once again, just like we do with our other definition, I want us to combine these fractions here. This one's a little bit uglier just because we've got so much more happening. So before I combine those, I'm actually going to distribute that out, and I'll just do that right here. So it's so I'm distributing this, so that turns into a 3x plus a 3h plus 4. And now, again, like I said, it's going to be kind of ugly, but bear with me, because we will need to know how to do it, I believe. So again, common denominator, so I multiply this and this. So 3x plus 3h plus 4, and then we're subtracting, and then I'm going to multiply this and this, because again, you want to find a common denominator. That's the easiest way for us to do so. And now our common denominator is just going to be these two multiplied, just like usual. And I know this is a lot. The other one was a lot as well, but I know it's a lot, and I know it's a little intimidating to look at. But again, what we're going to do is we're just going to FOIL these out and combine any like terms, because I'm confident that something will cancel out. So I'm going to write it over here. So I'm first going to FOIL that. So it's going to be 3x squared plus 3xh plus 4x, okay, minus 6x minus 6h minus 8. And for canceling sake, I'm actually going to do, I see that we're subtracting, so I'm going to do a minus and my bracket just like I did before. And I'm going to FOIL this out, so I'm going to get 3x squared I see that I've got plus 4x. I'm going to try to line it up with stuff that I see is going to cancel out, right? Because if I'm subtracting 3x squared, I know these are going to cancel, but we'll get to that in a bit. So I've got my 3x squared plus a 4x, and then I'll do this next bit. So it's plus 3xh is what we just got there, because it's an h times a 3x. Plus 4h, and then I've got my negative 2, so it's going to be minus 6x minus 8. So this is really interesting. Hold on. Did I mess something up? Just want to double check. It's going to be plus 4h. I did. Yeah, okay. So what we're going to see is, because we're subtracting all of this, I know those are going to cancel, 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 and those are going to cancel. So what this turns into is just a negative 6h minus 4h, or just negative 10h. And if we come back in and plug that in, that says the limit as h approaches 0. Remember, this is what we just FOILed out up there. So that's a negative 10h over that atrocious little x plus h minus 2 times x minus 2 all over h. And now I see these h's cancel, lucky us. So now it's just this. And we'll see that this is really, really close to what we got over here, right? And we know that when we actually plugged in the x for the t there, that became negative 10 over x minus 2 squared, right? Because that would be an x minus 2 times an x minus 2. So it turns into the x minus 2 squared. And now we see as h approaches 0, we just plug in a 0 for the h. So this turns into negative 10 over x plus 0 minus 2. So just x minus 2 times x minus 2. And look at that. It's the exact same thing. So that just kind of shows us, once again, that our derivative is this right up here. And so now they're asking us for what that derivative is. And we see that obviously we have no x's in our numerator, so it's going to be a 0 plus a negative 10. And it's over an x minus 2 squared, just like we found. All right, let's try number 4 now. This one is a pretty short one. It says if f of x equals this, we want to determine the intervals on which it is differentiable. So the first thing I notice is that there's a 2x to the 7th, which the domain of that is obviously going to be all real numbers. There's no reason that any x value would be outside of its domain. So I know that this has a domain of all real numbers right here, but then it's plus this right here. And remember, by our exponent rules, what we see here is that this 9 minus x to the 5/2, that's the same as the square root of 9 minus x to the 5th, right? Because we've got that 5th power and then we've got it over that half. So that's the same there, which means that in order to figure out which intervals f of x is differentiable, I need to figure out which numbers are inside and outside of my domain. Well, I know that if I subtract a 9, that's going to get me 0, which is valid. 0 is in our domain, which means that I can include a 9. But if I subtract maybe a 10, right, that's going to get me a negative in my radical, which is going to be undefined and therefore outside of my domain. So I know that x cannot be greater than 9. So it's going to be less than, but I know it can be equal to, so it's going to be less than or equal to 9. And we can double check that. If I plug in any number smaller than 9, maybe an 8, that'll get me a square root of 1 to the 5th, which is valid, and so on. And you might say, well, we could also write this as 9 minus x to the 5th inside of that square root. Unfortunately, that doesn't change anything for us, simply because this is an odd exponent, which means that if there's a negative inside of this, it's going to stay negative once we apply that exponent. If that was an even exponent, say we had 9 minus x to the 4th inside of that square root, then our domain would be pretty different, right? Because that would turn whatever this is even. Because even if I plugged in a 10 there, that would be a negative 1 to the 4th, which is just 1. So I'd get the square root of 1, which would be valid. But that is not the scenario we have here. So we see that x cannot be greater than 9, but it can be any value less than or equal to 9. So our domain is any x less than or equal to 9, which means that it is differentiable from negative infinity to 9 inclusive. Let's try number 5 now. So we want to figure out whatever this value a is. Wait a second, there is no a. Hold on. I think that's supposed to be a. Sorry. So we want to figure out whatever this value a is, given that f of x equals 2x to the 3rd, and f prime of a equals 24. Well, the first thing we want to do is we want to figure out what f prime of x is. Well, based on our power rule, I can just bring this down in front. So that's a 3 times a 2. Now times x to the 3 minus 1, which is just 2. So our f prime is just 6x squared. That's our derivative. So I need to know what a would be in this case, where a plugs into our x, right? That makes our f prime equal 24. So I need to know 6x squared equals 24 when x equals what? Well, if I just divide by 6, that gets me an x squared equals 4. So x equals 2, which means f of a is, or f prime of a is f prime of 2. So a equals 2. Oh, all right. These next two are going to be tricky ones. They're more of a conceptual problem. So it says find the rate of change of the area of a square with respect to its side length x. Okay, so this is the derivative of a with respect to x. Well, if we know that the area of a square, so a equals x squared, right? Just by the definition of the area of a square, of a square, they all their side lengths are the same. So the area is just x squared. So all we have to do is take the derivative of this. So dA with respect to x is just going to be, based on that power rule, it's going to be 2 times x to the 2 minus 1, or just 2x. So that's our answer. Let's try the next one, which is a similar one. Oops, didn't mean to do that. So this next one's a similar one, although slightly trickier. It says find the rate of change of the area of a triangle with a constant height of 4 with respect to its base b. So, important for us to remember that the area of a triangle is going to be 1/2 times base times height, right? What they're telling us here is that the height of this triangle is 4, so we know it's got a constant height of 4. So in this case, our area is 4 times 1/2, or just 2b. So if we want to find the derivative of that with respect to b, well, I know this is a power of 1, so we could use our power rule here if we were confused, but the derivative of this will just be 2, right? Because it's going to be a 1 times a 2, and then I would subtract 1 from my numerator, would just get me b to the 0, which is just 1. So our answer is 2. I hope that makes some sense. Number 8 is a tricky one, although in my opinion it's pretty fun to do. So it says 2 birds are flying from the same place, so it says they start at the same point. And bird A is flying south at a speed of 25 meters per second. Okay. And bird B is going west, this way, at 10 meters per second. Obviously, these lines wouldn't quite be the same, but that's not the point. So we want to figure out at what rate is the distance between the 2 birds increasing. Well, I know that if I want to find the distance between the 2 birds, then I know that that's going to be this right here, right? And we'll represent that with D. So the distance between the 2 birds is whatever this length here is. And instead of meters per second, we're just going to use an x in that case to represent our meters per second, because that's our time, right? So so A is moving at a speed of 25x, and bird B is moving at a speed of 10x, okay? So in this case, you know, this is a right triangle because one's going west, one's going south, so they're perpendicular to one another, which means I can apply my Pythagorean theorem. I know that this length is going to be whatever B is at at point x, and this length is going to be whatever a is at point x. So I know that d squared is equal to a squared plus b squared, which gives me d squared equals 25x squared plus 10x squared. And we could go ahead and square those and combine like terms. I know 25 squared is 625, so it's going to be 625 times x squared plus 10 squared is 100 x squared. So d squared equals 725 x squared. And then if I want to find d, that's obviously going to be the square root of whatever that is. And we could leave it here. But I know that there's there's things I can pull out of this radical, so I'm going to do that. So let's figure out, I see that 25 is definitely a factor of 725. Let's see, 725 divided by 25. Well, I know that's 125, and then there's 4 25s and 100. There's 7 of those, so it's 28. So that's going to be, so 725 is equal to 25 times 29, which means since 25 is a perfect square, I can pull that outside of my radical. So d equals 5 times the square root of what's left, is that 29 x squared. And I can also pull out this x squared, right? Because the square root of x squared is just x. So it's a 5x times the square root of 29. But we're not done just yet. That's the trick bit. So that's our distance at any point, but we want to find at what rate is the distance between them changing, which means now that we have our distance, we need to take the derivative of it with respect to x. So if d equals 5x times the square root of 29, well, this is constant coefficient, and so is this, so we're just really taking the derivative of x times whatever these are. So the derivative of x is just 1, so this turns into a 5 times a 1 times this, or just 5 times the square root of 29. That is our answer. And because they were going at a rate of meters per second, I believe this would be meters per second squared, but don't quote me on that. Number 9 has a really simple instruction of reduce and evaluate. And this one's actually based on rules that we've already worked on in this class. So if we remember, we learned in earlier chapters of our textbook that the limit as x approaches 0 of e to the x minus 1 over, wait a second. I feel like I'm misremembering, actually. Give me one moment. Okay, so I was misremembering, but that's okay because I figured it out. So this one is trickier than I thought it was, but that's okay, because what we want to do first is, so we know the limit as x approaches 0 of 3x minus 7 over. So this is what we are looking for. And so the first thing that I'm going to do is I'm going to factor out that 7. So that's going to get me limit as x approaches 0 of 7 times e to the 3x minus 1. And I'm actually going to move the 7 in front of my limit, just so that we don't have to worry about it. So I'm going to move that in front because it's just a coefficient, so I'm able to do that. So it's 7 times whatever this limit is. And now, I know this isn't the easiest to recognize, but this right here is a perfect cube. And so we can factor that out, right? So I'm going to factor it out. It's going to be an e to the x, right? Because it's that cube there. So it's an e to the x minus 1 times, that's going to be e to the 2x plus e to the x plus 1. And I just want to show us really quickly, I figured this out the other day actually. So if I have, let's say I've got x to the 4th minus 1, that's going to be x minus 1 times, and then I go to the next power down. So I go x cubed, and then I go I go x cubed plus, oh, no, sorry. I got myself confused. So let me redo that. Sorry. So let's say I've got a cubed minus b cubed. Or, sorry, to the 4th. I want to do to the 4th. So a to the 4th minus b to the 4th. What that's going to be is it's always going to be an a minus b times. Now I'm going to go to the next power down of my first term. So I'm going to go a cubed. And we're starting at a power of 0 for this. So a cubed times b to the 0 is just a cubed. And then I'm going to go one more power down. So I'm going to go a squared. And that's going to come up. That's going to be times a b. And then that's going to be plus an a, because I go one more power down, times a b squared, because I'm going one more power up. And then it goes a to the 0, which is just 1, plus b cubed. And it's this nice little mirrored pattern here. And that works for anything. So if I did like a to the 7th minus b to the 7th, it's going to be the same thing. It's going to be a minus b, and then it's going to be that same exact pattern. So it's going to be a to the 6th plus a to the 5th b plus a to the 4th b squared plus a to the 3rd b to the 3rd plus a to the 2nd b to the 4th, and so on until we get this. So what we're seeing here in our case is that we've got a cubed minus b cubed, in which case our a equals e to the x and our b equals 1. So what we're going to have is we're going to have e to the x minus 1, right? Because that's our a minus our b, times, we got e to the x to that next power, so e to the x squared, which is e to the 2x, times 1 to the 0th, and then e to the x to the first power, which is just e to the x, times 1 to the first power, which is just 1, and then e to the x to the 0th power, which is just 1, times 1 squared, which is just 1. And that's how we got this factor bit right here. We see that that's the exact same as how we factored that out. So now, oops, not what I meant to do. So now we know that this is 7 times the limit as x approaches 0. We know our x to 3, or e to the 3x minus 1 is equal to this. So I'm going to plug that in. E to 2x plus e to the x plus 1 over e to the x minus 1. And I see that these cancel. Lucky us. So now I keep going. It's 7 times the limit as x approaches 0 of just e to the 2x plus e to the x plus 1, which if I just plug in the 0 for all those x's now, I get 7 times, well, e to the 2 times 0 is e to the 0, which is just 1, plus e to the 0, which is just 1, plus 1. So this turns into a 7 times 3, or 21. So our answer is that the limit is 21. Let's try number 10 next. Let's see. So this is just kind of based on our sum rule, which basically means that if you're adding 2 bits, so if I've got this 3x to the 5th plus x to the 4th, right? If I want to take the derivative of this, it's just going to be the derivative of this plus the derivative of this, because we're adding. It only becomes complicated if we start multiplying or dividing, really. So the derivative in this case, I know the derivative of this is going to be 15x to the 4th. So I'm going to put 15x to the 4th. And the derivative of this is going to be 4, because I put that 4 in front, right, because of our power rule. X to the 3rd, because I subtract 1. So that's a 4x to the 3rd plus 3 times 2 6x squared plus, put that in front, so 10x plus, and this is power to the 1, so by our power rule, it's going to become 0, so it's just 10. Because this is a constant, it disappears. The derivative of a constant is 0, so this is plus 10 minus 0. It just disappears. And we see that we don't have anything times x to the 5th, so we'll put a 0 there. And that's all that this question wants from us. Let's see, how many more questions do we have? Just a few. Okay, 6 it looks like. So for number 11, we have g of z equals 3 sine of z plus 7 cosine of z minus 8. Now, remember, if we've got a coefficient, it doesn't impact our derivative, right? The derivative of sine of x, we know, is cosine of x. So if I want the derivative of 3 sine of x, that's the same as 3 times the derivative of sine of x, because it's just a constant coefficient. So that's going to be this. So we know that first bit is 3 cosine of z. Now we want to take the derivative of cosine, which we know is negative sine. So it's going to be a negative times that 7, so negative 7 sine of z. So I can actually change that plus to a minus because we're adding a negative. So I'm just going to subtract 7 sine of z. And like I said before, the derivative of a constant is 0, so it's minus 0, which means we don't have to write it. The next one is trickier because in this case right here, we aren't adding, we're multiplying. So what we have to use is the product rule, which we should have learned in this chapter. And the product rule tells us that if we have one term, we'll call this u, and another term v, the derivative, we'll say, I don't really know how to write that. So we'll say that the derivative of this is going to be, so the derivative of uv, we'll say prime, I don't really know how to write that, is going to be the derivative of the first term times the second term plus the first term times the derivative of the second term. So in this case, our first term is that sine of x. So we know, so I'm just going to ignore our coefficient right now because we don't need to worry about it until after we've found that derivative, right? So it's going to be 3 times whatever that is. So in our first term, our u is that sine of x. So the derivative of sine, we said was cosine, right? So derivative of sine is cosine, so it's going to be a cosine of x times v is cosine, so it's just, ooh, don't go away. So it's just cosine of x times cosine of x. And then we have to add this next bit. So our first term is sine of x times the derivative of our second term. So the derivative of cosine of x is negative sine. So it turns into this, and combined like terms, obviously cosine times cosine is cosine squared. And well, we see that's a negative, so I'm going to put that negative in front. And sine x times sine x is sine squared. Remember, we had that 3 in front. So we've got 3 times cosine squared minus sine squared x. And we can distribute that, so that would be, oh, sorry, that's a negative 3. My bad. So it would be a negative 3 cosine squared of x. Negative 3 times negative sine squared is going to be a positive 3. Okay, and now we've just got this last term, which we're subtracting, so that's adding a negative, so our sum rule, or we could use the subtraction rule, but it's the same thing. Which means that we just have to take the derivative of this now. We know the derivative of cosine is negative sine, so it's minus a negative sine, or just plus sine of x. All right, and that's our answer. That's that whole derivative there. This next one is a little uglier just because we've got our secant x in here. So again, this is the product rule because we're multiplying these two pieces. And in this case, this is our u term, this is our v term. Again, it's the derivative of u times v plus u times the derivative of v. So the derivative of 2x minus 1, well, I know that derivative of x is 1, so it's a 2 times a 1, and then that's a constant, so it's a 0. So the derivative of u is just 2. And then our v is that 3x plus secant x. We're just going to write it like that for now. And now we take our first term, which is our u, so 2x minus 1, and we multiply it by whatever the derivative of v is. Now we've got our sum rule here, so the derivative of this part is just a 3. But then the derivative of secant x is a little bit different. I believe this should be in the textbook in section 3.3. So the derivative of secant x is actually secant x times tangent x. So that's going to be what's in there. So now we could try to FOIL it out, but for time's sake, I'm just going to leave it like this because this is our derivative. So, oh, I will actually distribute that too. Oh, oopsie. It never erases what I want it to. Yeah. So I'm going to distribute that too, but that's the only thing that I'm going to distribute. Although I can take away those parentheses because we're still adding. But for this bit, I need to be multiplying still. Okay. And that is our derivative. All right. Now for number 14. Obviously, we could use that definition with our limits to find this, but we're just going to use the quotient rule, which is similar to our product rule, but just a little bit different. So the quotient rule tells us if we have this bottom term and this top term, the derivative of this quotient is going to be the bottom term times the derivative of the top term minus the top term times the derivative of the bottom term over the bottom term squared. And that feels a little bit tricky to remember, I feel like. The way that I learned it, I remember it sort of rhythmically in my head as, and this is going to sound a little bit silly, but I remember it as low d high minus high d low over low low. What that tells me is that's low is my bottom term, because it's down low, times d high, so the derivative of the high term, minus high, so my high term, d low times the derivative of my low term, over low low, which is just my low term times itself, or squared. So you'll probably see me write this a lot when I'm doing quotient rule, because that's how I remember it personally. But just remember it however helps you best. This is a slightly more formal definition given our current example. And so let's further evaluate that, right? So we've got 2x plus 5 times the derivative of 9x plus 1. Well, the derivative of 9x is 9, and that minus 1 disappears because it's a constant, so it's just a 9. And then minus our high term, which is 9x minus 1, times the derivative of our low term, which in this case is just a 2 over 2x plus 5 squared. And we can, obviously, they're going to want us to simplify, combine like terms so that we can get it in terms of this. So I'm going to distribute that out. So it's going to be an 18x plus 45 minus, distribute that, that's going to be minus an 18x minus a negative 2, so plus 2 over 2x plus 5 squared. Combine like terms. These cancel, So we've just got 45 plus 2, which is a 47 over 2x plus 5 squared. Our a is going to be 0, obviously, because we don't have an x term anymore. Our b is just that 47. And our c is a squared, because it's 2x to the 5th squared. All right, now for number 15, they just want us to find the derivative, and they want us to find the value of the derivative at x equals -1. So again, we're going to use the quotient rule, which is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So low d high minus high d low over low low. So in that case, that's going to be our low, which is x cubed minus 4 times the derivative of our top, which 5x squared minus 2. Well, I know with my product rule, I'm going to put that in front, so it's a 10x minus 0, so 10x, then minus my high term, times the derivative of my bottom, which is going to be a 3x squared in this case, over x cubed minus 4 squared. Okay, now, honestly, we could just plug in the -1 to this. We don't actually have to simplify. It might be easier for us to simplify, but that's extra time. So I'm just going to go ahead and plug it in as is. So that's going to be a -1 cubed, which is just -1 minus 4 times 10 times -1, so -10 minus -1 squared is 1 times 5 minus 2. -1 squared is 1 times 3 over -1 cubed is -1 minus 4 squared. Okay, so now I've got a -5 is what that is, times a -10 minus 3 times a 3. So that is a 50 minus 9 over, that's a -5 squared, which is 25. So let's see, we get 41 over 25. All right, and now I think we're on our last question. Yep, this one is a tricky one though. So we're given that L equals tangent of G over G to the 4th. So we want to find the derivative of L with respect to G in these terms, and trust me, it'll work itself out that way. So let's just go ahead and figure out what the derivative of L is with respect to G. So in this case, our quotient rule helps us again. So we'll take that bottom term, G to the 4th, times the derivative of our top term. And again, this is in our textbook, I believe in section 3.3. It might be in 3.2, but I think it's in 3.3. The derivative of tangent is just secant squared. So this is going to be secant squared of G, and now minus our top term times the derivative of our bottom, which is 4G cubed, all over G to the 4th squared, because that's just what our quotient rule is. Now, that's already pretty close to these terms. We just have to manipulate it a little bit. And so we know we see we've got that secant and that tangent, but we see that we don't have a G in there, so we want to make sure we get our G out. And what I can actually see here is I can factor out a G cubed. So I factor out a G cubed, and that turns into a G times secant squared of G minus this 4 times tangent of G. And that's all over G to the 4th squared, which is G to the 8th. And because I factored this out, I can cancel that out, which turns that into just G times secant squared G minus 4 tangent of G. Obviously we're subtracting there, so it's going to be G to the 5th, because 8 minus 3 is 5. And now we see that this is actually exactly in these terms. We see we don't have a coefficient in front of our g, so a equals 1. G to the b, our power here is obviously a 1. So then we've got secant squared of g plus c tangent of g. Our c in this case is that -4, all over g to the power of d. We see d is 5. I do believe that was our last question. Yeah, I hope that this made sense. We're obviously delving into some trickier territory than we've been in up until now, but it's nothing that I don't think we can handle. Yeah, so I hope that this video was helpful. If you're confused on any of the derivative rules, once again, Khan Academy, Google are your friends, and they're stated all throughout our textbook, I believe, especially in the current sections that we're working on. And that is it. Thank you for watching.